Welcome everyone. Today we're going to discuss RF link budgets. What does that mean? We're going to explain in detail. It means that you need to get the right signal losses when you're constructing a test bed. And by right, I mean they will correspond to real life. And that's what we're going to discuss today. Let's introduce our speakers. We have again with us today our CTO, Lee Chinitz, who has spent many years in the industry and not just in Wi-Fi, but other wireless technologies, UMTS, CDMA, femtocells. He has worked with the FCC and with standards bodies like IEEE, TIA, ITU, and Wi-Fi Alliance. Lee holds 20 patents and has a PhD in physics, along with other degrees. Radha Cannon is our systems engineer. She's based in Dallas. She works extensively with our system on automation scripts and a variety of complex tests. So she will be with us today to show us some live demos. And last but not least, Anna Stepovich, who has just joined octoScope, and this is her first tutorial with us. Anna is our VP of Systems Engineering. She's based in our San Jose office in California. She's an experienced professional who has been spending time in engineering, customer support and operations, worked with mainstream companies in communications, including Nortel, Ericsson, and Sprint. And so Anna will, she comes from Belgrade actually, and that's where she got her EE education. So with that, I'm going to hand it off to Lee and we'll get started.
All right. Thank you, Fanny. And yes, hello everyone. So welcome to the 5th in our seminar series related to wireless testing. We're glad that you could join us today, and we hope that some of you are actually joining us again. So in some of the discussions we've had as part of this series, we've discussed some basic testing techniques like the use of a turntable for various reasons. We've also discussed more esoteric things like OFDMA testing, fundamentally around Wi-Fi 6. Today we're actually focusing in on a really nuts and bolts topic, which is the concept of a wireless link budget. So,
excuse me, Lee, are you switching slides? Because we're still sitting on this presenter slide.
Yeah. Okay. Thanks. Yeah. Okay. I'll move to this slide for that this part then. Thanks. Yeah, we're gonna talk about a wireless link budget. So why did we choose to do this? As Fanny already mentioned, it's because wireless link budgets are really the basic language of wireless testing. And, you know, we find that not everybody is actually very familiar with the concept of a wireless link budget. And even those people who are not always clear how to translate those concepts into how to talk about a link budget inside something like an octoScope personal wireless testbed. So, you know, when you talk about link budgets, you inevitably hear things like, you know, oh, well, we have, you know, this many dB of path loss over the air, or if we stick this thing in, we're going to get some more dB of path loss, or if we put on that thing, we'll get some more dB in the link budget. So we thought it would be useful to try and clarify what all that means and really get into some details of what that means inside a personal testbed like the octoScope testbed. Okay, so, all right. So to start off with, we need to introduce the concept of a wireless channel. So when people talk about the wireless channel, they're talking about the fact that, you know, radio signals go from a transmitter to a receiver, and they can get there in a number of ways. They can get there directly, and I've just labeled this one space. We'll talk about that a little bit later. And they can also get there, you know, via other things that happen to be around. The ground is a big one, depending on what your, especially what your technology is. That's a key one in things like television wireless and, you know, outdoor cellular systems. And then there's all the other stuff that's going on in the environment. that the signals will interact with as they move from the transmitter to the receiver. So all that stuff, when you put it together, is results in the fact that the transmitted signal will actually reduce in strength as it moves from the transmitter to the receiver. And that's what we mean when we talk about path loss. When people talk about path loss between the transmitter and the receiver, that's what they're talking about. Okay, so I have this slide here just to warn you that I have the next slide coming up is got more math in it than the rest of the whole presentation put together. But for me, I could not help getting into this a little bit because it's kind of the basic principles of link budgets. But for those of you who are not interested in math, you can tune out for exactly one slide. So in that first slide, I talked about the fact that signals do get from the transmitter to receiver. They can do it without interacting with anything. They just travel through space. And even traveling through space, the signal will get weaker as it goes from the transmitter to the receiver. So why is that? The basic principle here is that energy is conserved. This is a fundamental concept in physics, and it's really the kind of the basic point around path losses. When a transmitter transmits energy, you can think about the simplest possible way that it could do that would be to transmit energy in a sphere. So just in every direction all at the same time. And as that energy moves out, the sphere gets bigger and bigger. So if you imagine putting a little patch on the outside of that sphere, and the amount of energy that you receive through that patch is what you see in your receiver, then you can imagine how as the energy moves out through space and that whole sphere gets bigger and bigger, that patch is seeing less and less of the total. And that's why the kind of the fundamental path loss that people, everybody understands is that path loss decreases as the square of the distance between the transmitter and the receiver. That's the kind of the basic principle of free space path loss. And that one's kind of easy to understand because of that model that I just said. If you just think about stuff going out in the sphere, that's how it works. There's another one, though, that, once you understand path losses, it becomes kind of a basic thing that you always think about, which is that the path loss also increases with the frequency. That one I think is actually less obvious, and it's part of the reason I wanted to do this slide, just to make sure that everyone understands why that is as well, right? Because if you think about it, why does it matter? The energy still goes out in a big sphere, and it doesn't matter what the frequency is. So conservation of energy is still the same. If you put a big sphere around it, you're going to suck up all that energy, and your little patch is going to still see the same amount. So why does it matter about frequency? In this particular case, it matters because you have to think about what you're actually receiving it with. So that little patch example that I gave before is kind of a theoretical idea that you can just grab all the energy in your little patch. But actually, if you think about what a real receiver will look like, it'll be made up of an antenna. And antennas actually decrease in size as the frequency goes up because the effective area of the antenna is related to the frequency. So it looks like this. This is the actual equation for the effective area of an antenna. And you can see that it's proportional to the wavelength or inversely proportional to the frequency squared. And so, wavelength sizes, depending on the frequency you're operating at, get smaller and smaller as the frequency goes up. So it can be measured in feet for very low frequency wavelengths and measured in inches or centimeters as you go up and up in frequency. So that is what gives us the very famous, actually, result for path loss. What this equation says is that the amount of energy you receive is related to the amount of energy you start with at the transmitter, and then it's inversely proportional to the distance squared and the frequency squared. And if you want that in the more commonly used format in dB, it looks like this one, where the frequency is in gigahertz, the distance is in centimeters, and this will give you the path loss in dB. All right. Anyone who took a break for that slide, you can come back now. So what are all the G's in that last slide? So the G's actually refer to gain. So what does that mean? It means that antennas actually don't do what I said typically, right? They don't transmit energy in all directions at the same time, all the time. You can actually point the energy in a specific direction like a flashlight, and that's called gain on the transmit side. Receivers can also have gain, and that's a little bit like if you imagine a person using a little ear horn to hear better in one specific direction. Kind of point the horn at what you want to listen to, and you hear better. So you can have gain on the transmit side. You can also have gain on the receive side. When we talk about real antennas, then we're not talking about these things that transmit in big spheres. We're talking about antennas that transmit in specific directions. One of the most classic is just a what's known as a dipole antenna, and they look like this. I'm sure most of you have seen them before. And they, again, don't transmit in complete spheres. They transmit in what looks a bit like a donut. And you can see that picture here. I think mathematically it's called a toroid, but that's what it looks like. So it's transmitting kind of along, mostly out in this direction along the edge, and not really at all up and down to the top and the bottom. They also have polarization. So when you have a transmitter and receiver looking to talk to each other, you usually want those antennas to be in the same orientation, because if you don't have them in the same orientation, like shown here, one up and one to the side, then you can get a lot more loss in your link budget. So what does that look like then if we just think about what path loss then looks like as a function of distance? It looks like this. So that equation that I showed you before for free space, what's known as free space path loss, which really only includes the effect of distance, so going as 1 over the distance squared, and the frequency going as 1 over the frequency squared, looks like this blue line on this chart. So this is path loss on the vertical axis, and distance in meters on the horizontal. And then you can see what that looks like. Now, there are a lot of other models. So when I talked about the whole idea of a link budget at the beginning, I said there's that the signals don't go only through free space from one to the other, from the transmitter to the receiver. They're bouncing off the ground. They're bouncing off stuff in the middle. That stuff is going to be different depending on the environment that you're in. And there are many, many models of path loss, and we show some of them in this chart. But the important thing actually is, for our purposes here, is to just realize that mostly they have the same basic shape. They have this logarithmic shape as a function of distance. You get a lot of path loss early on in the as you separate the transmitter and the receiver. The path loss between the two rises quite quickly, and then it flattens out. And you may get some more path loss in these different models than you will get in free space, but roughly it all has the same basic shape. By the way, this particular model is available on our website in our resources section. It can be downloaded. Now, you can have models that I just talked about, some that try and say, well, what would it be like if I was in a crowded office environment? What would it look like if I was outside in an open space or in an urban environment? So there are models like that, and then there are also there are a lot of measurements that talk about the additional path loss you get if you add some specific thing between the transmitter and the receiver. So suppose you have a transmitter and receiver separated by a pane of glass. What does that look like? Well, that pane of glass will affect the signal level that the receiver is going to see by a certain amount, depending on the frequency. And that is actually shown in this chart here. So you have the additional attenuation that you get between the transmitter and the receiver as a function of frequency. And there is, again, a lot of information. People do measurements of these things all the time. And it's incredibly useful if you want to be able to put together an actual link budget, an actual wireless link budget. So I have a reference here for some Ofcom measurements that were done. But again, there's many, many more pieces of information out there around these kinds of things. Okay, so with all that said, we have transmitters, we have receivers, we have the channel and path loss, we have stuff that is causing more attenuation. So how does that all come together to make a link budget? I see your hand, Naveen. Let me finish this slide and then we'll go to your question. So what's a link budget? A link budget then describes how well a transmitter is able to be received as the signal flows across the wireless channel. So at a high level, we can think of it as a person speaking, so that's the transmitter, another person listening, that's the receiver, and the thing that this person is saying has to make it from the person speaking to the person listening, and there could be a whole bunch of stuff in the way. So if this person yells the word link budget, then by the time it reaches the person listening, it's a much quieter link budget. And if everything works out, that person can still hear what the person speaking said. So Naveen, what was your, is somebody gonna unmute Naveen to ask the question?
Yeah, Lee. So my question is, so you have shown the data just one slide before this slide, and that data is taken from our own test bed, or it's a general data which is available somewhere?
Yeah, this is general data. So usually what people will do is, set up tests where they, you can see what's here, right? They'll put a piece of glass, and in this document, when it says wood or glass, it will be much more defined. It'll be like, a certain type of glass, and it will be, whatever it is, a centimeter thick or something.
So, do we have something in our setup to simulate something similar to path loss?
Yeah, so we're going to talk about how you put all this together in our setup. Okay. Once you have this information. So yeah, let's see if we answer your question. That's what we're trying to get to. We're trying to get to an understanding of how all these pieces come together to make up something that we can then model in our test bed. Okay.
Yeah, thanks.
So, yeah, let's wait and see. You can ask the question again later if we didn't manage to answer your question. Okay, so in that previous slide, I talked about that person, speaking, and you can see that person was shouting in the picture that I showed to represent a person essentially speaking as loud as he possibly can. So let's translate that a little bit into wireless. So in radio, right, the person speaking is the transmitter, and the degree to which that person can speak loudly is what's known as the allowed transmit power. So there's actually a lot of reasons why the transmit power might be one thing or another, right? A certain kind of wireless link might demand high power, and another kind of wireless link might not. And the decision may be based on the actual service that you're trying to provide. But at the end of the day, the one thing we know is that the maximum power level is set by regulatory restrictions. So no matter where you are, there's going to be some regulatory body. So here in the United States, that's the FCC, and in various in other countries and regions around the world, you'll have different regulators, but they will tell you what's the maximum transmit power you can use. So for example, if we're talking about Wi-Fi and the 5 gigahertz band, it's not really Wi-Fi, actually, I shouldn't say that. If you're talking about the 5 gigahertz band in the United States, then we have the band broken up into a couple different regions known as Uni 1, Uni 2, and Uni 3. And you can see down here at the bottom that there is a different amount of transmit power allowed in each of those bands. So the low one, Uni 1, is actually only allowed in the United States for indoor operation. And you can see that the transmit power is lower than the other ones. It's 50 milliwatts. Whereas Uni 2 is 250 milliwatts, and Uni 3 is 1,000 milliwatts. So very different, powers allowed in each one, meaning that the transmitter side of our link budget equation is going to be very different. When you're looking at doing testing, that's something that you need to always be aware of. There's a new 6 gigahertz band that is the talk of the Wi-Fi industry these days. We have a whole bunch of new unibands, at least again in the US. We've called them Uni 5, 6, 7, and 8, and I think has been mentioned many times in many different venues. It's a lot of spectrum. You can see here that this is only Uni 5, Uni 6, and part of Uni 7. Then we have the rest of Uni 7, Uni 8. So it's a lot of spectrum. In fact, if you take Uni 5, 6, 7, and 8 and you add those up, you get a total of 1.2 gigahertz, 1,200 megahertz of spectrum. And the powers there look like what's shown in this table. So the way the regulatory regime has worked out here in the US, we're actually able to use these channels, these 6 gigahertz channels, for kind of 2 separate ways of using it. One is what they call low power use and only indoor. And the rules are the same for all these bands. Basically, depending what bandwidth we're operating at for low power indoor, we have different amount of transmit power that we can use. And then the other way that we can use those channels is in what's known as automatic frequency coordination controlled. So it's controlled by essentially a frequency coordinator that will help avoid interference between systems. And when we do that, basically the transmit power, the total maximum transmit power for all of these is the same at 36 dBm. FYI, there's still some ongoing activity, at least in the United States, about these. These numbers may change, so this slide may not be exactly right in the future, but it's correct right now. But again, there's still some ongoing activity. And now, we just talked about all that stuff in terms of dBs, and I'd mentioned dBs before, and I thought it might be useful to for anybody here who's not a wireless engineer by training, you may kind of wonder why is it that we always talk about all this stuff in dBs, right? Instead of saying something like, hey, you can transmit, 200 milliwatts, people will say, well, you can transmit 23 dBm. So why is that? Part of the reason I want to do this too is because I always like to, acknowledge this first point, especially for people who aren't that familiar with radio. Radio is just amazing when you think about it. If you, again, speaking in dB here, just for a second, if you look at a typical, let's say, Wi-Fi access point, you might be talking usually about a transmitter that can transmit at something like 20 dBm. That's a typical thing, like 100 milliwatts. And if you look at the receive side, receivers can receive signals down as low as, say, negative 90 dBm. If you translate those into linear power units, that's what's on this line here. We're talking about 100 milliwatts and whatever this number is. Those things are different by 11 orders of magnitude. So you can see it's below the transmitted signal. The received signal is below the transmitted signal by 100 billion times. Again, I just find that amazing. But as you can imagine, it would be really impractical to talk about things, when you're actually working day to day, talking about these kinds of ranges. It's just impossible. So that's why people use dBs. It's a much more convenient mechanism for referring to these dramatically different scales of numbers that we have to deal with in radio. Okay, so let's get to link budgets now. So I hopefully we've kind of explained all of the components of a link budget. But, you know, at the end of the day, it just talks about our transmitter, so our guy screaming, and our receiver, which is the person listening, what we want to look at is kind of the full range of that possible link budget. So what's the furthest we can possibly get? So again, I just mentioned these numbers on the previous slide. If you have a transmitter at 20 dBm and a receiver at negative 90 dBm, that's, again, 11 orders of magnitude. And when people talk about that link budget, they'll talk about that as 110 dB. So that the full link budget is 110 dB in that case. A picture like this is a very good way of thinking about a link budget. So again, we have we start off at the top here with transmit power, and then we have the full link budget going all the way down to the bottom, which is our negative 90 dBm. That's the minimum possible signal that we can receive and still make any sense of it. Anything below that, we can't hear it. So that's the full link budget. Now, one important thing to know is that the link budget itself is not exactly the same as the operating range. And the reason for that is that there's actually a portion of this link budget right near the transmit power that's referred to as the saturation region. And the saturation region really just reflects the idea that it's actually possible to be too close to the transmitter. And you can imagine this, again, same kind of model that I was talking about before. If you just think about this in terms of sound, you can understand how it's actually possible to be too close to the transmitter. If that transmitter is really loud, you will be overwhelmed by that sound. And that's exactly the same thing that happens to a radio receiver. The radio receivers are not built to receive signals that are too strong. So there's really what's known as an operating region between the kind of the highest level signal that a receiver is built to handle and the lowest one. And in Wi-Fi, the range is something like this: negative 30 dBm at the top side, down to in the neighborhood of negative 90 dBm at the bottom side. So the factors then that will influence the total range have to do with the path loss that we've hopefully been describing this whole time. Multipath, so that's part of what I mentioned before, signals bouncing off the ground and off of other stuff. We also had a seminar on multipath, actually our first seminar, number 1 in this series, talked all about multipath. Other fading caused by other things moving around in the environment, or the transmitter and receiver moving relative to each other. Obstructions to the Fresnel zone, which I will not get into, but has a little bit to do with, mostly talked about in terms of the concept of the ground, if you're using the ground. Whatever scheme you are using in order to receive the signal, so that's known as the modulation scheme, and that's directly related to the receiver sensitivity here. So, very simple modulations are easier to receive. Very complex ones are harder to receive. And then other techniques in terms of sending the signals from the transmitter to the receiver, for example, things like beamforming and multiplexing and diversity. So other gains, when I mentioned all the G's before in the link budget, these typically come in as G's. All right, so let's get to the question that we really wanted to get to, and kind of Naveen's question here. What does this mean for our test bed? So let's actually start with one simple fact. Consumers love mesh. If you look now at something like Amazon and just take a look at Wi-Fi products, you will see tons of mesh products out there. So they're very popular in the market, and because of that, we certainly have a lot of people who want to be testing them in a test bed like ours. So let's talk now about this whole concept of link budgets in the context of doing mesh testing. So when we're setting up tests in a test bed, what we want to do is emulate real world scenarios, right? We don't want to people don't want to test things that don't somehow relate to what customers will actually have to deal with. So a big part of that is trying to figure out how to emulate how far away devices will be from each other and what the channel between them looks like. So let's think about this, right? Let's imagine that we want to emulate a setup like this. So this is some home. And we can imagine a mesh setup here. So you can see we've got a little red AP here. We've got a blue AP stuck in this corner. We've got a green AP. So this is a 3-node mesh system that has been set up in this environment. How do we test that? And what do link budgets have to do with it? One thing you can see is that, we can say, we can understand what the distance would be between these things. You can see 8 meters, 6 meters, 10 meters. We can see that there's some walls between them as well in certain cases. And, we have some sort of environment that this is in. Typically, this would be like a small home or small office environment. So what we can do is start by setting up these links, right? So we can estimate what the path loss would be based on some sort of model. Before we talked about free space, because that's the one that you always start with. But, as I said, there are many different kinds of path loss models. And there are models for, open areas, small homes, crowded offices, outdoor, all kinds of things. And then also, as I mentioned, there are measurements that tell you how much path loss you would get if you went through a wall of a certain thickness, made of a certain kind of material, whatever it is. So using all that material, all that information, we can actually translate from distance in this environment to path loss. So we can say, well, between red and blue, there should be 83 dB of path loss. Between blue and green, there should be 86. Between green and red, there should be 79. Okay, so now we know that. All right, so what does that mean? What do we do with that information? Well, we can now convert this to a test bed, right? So when we convert this to a test bed, what do? We actually take each one of those mesh APs and enclose it in its own isolated chamber. We connect those chambers using RF cables and antennas. And then we add attenuators onto each of those links so that we can program the total path loss between those devices in the chambers to be whatever we want it to be. So we can set it so that we have 83, 79, and 86 dB between these devices. And so, of course, once we do that, we don't even have to be in the location, right? The location now doesn't matter. We can set this up anywhere in one of our test beds. Then the question we have to ask is, how do we know in the test bed, right, that we've created a 79 dB link or an 83 or an 86? So there are a bunch of pieces that make up a link budget in the test bed itself. And that's what I'm going to describe here. And then we're going to show you a little bit of some demos of how we can understand those link budgets. So, the first thing that's going on is that we've enclosed our devices into these isolated chambers. So there's an over-the-air link now between the device under test and our testbed antennas. So what path loss should we use for that? To answer that question, we actually measured the path loss inside the box using dipole antennas, so with a well-known antenna pattern. And we have data on that. We measured that in the 2.4 gigahertz band. We measured that in the 5 gigahertz band. We measured it for different separations between the antennas. And when we plot that information, that's the blue curve here, against the free space path loss model, which is the one I showed way at the beginning in the math slide, for 2.4 gigahertz or 5 gigahertz, you can see how closely the measured data aligns with the free space path loss model. So we very comfortably use a free space path loss model for path loss within the chambers. It's extremely good model there. Then there are these other things in the link budget when we put it all together. We have, and I'll talk about that in a little bit, what those things are, what the other stuff is. But the point that I want to make here is that we have measured all of those. And actually, most of this information is just available directly on our website. I've got one example here. If you were to look at our attenuator, for example, you can see here at the bottom that we've got measurements for the loss due to that attenuator in 10 dB steps. And this is in the 2.4 gigahertz band. We do it in the 5 gigahertz band. We do it all over the place. So we have all this information available. So let's talk about some of the factors then in a link budget in the test bed. So we've done the over-the-air part now. We know that free space is an extremely good model for that. What about these antennas? Anyone who's used our test bed knows we have these high gain antennas that are very commonly used. So we know that as part of the link budget, they're going to contribute to those gain terms. So how much gain should we assign for these? Well, we have those measurements as well. What we're showing in this figure here is a measurement between dipole antennas at the bottom, and then we use the high gain antenna here shown on the top, and we can see that those gains those antennas give us about 10 dB more power than a dipole antenna would. So relative to a dipole, we've got about 10 dB gain there. We have multipath emulators. As I mentioned, this was the topic of our very first seminar. And if we take a multipath emulator and just put it in the link, not even using it to emulate multipath, just having it in there, switched to what we call our line of sight mode. This little image up above is showing that we are able to switch between the line of sight mode and the non-line of sight mode. So in that mode, we just get some loss just because it's in the link, and this is a measurement of that loss. That's what's known as insertion loss. So as soon as you insert something in the link, it's going to give you a certain amount of loss. And here's those measurements as a function of frequency. And then when we switch it on, as you can see here, I've switched it on. When we switch it on, we get the frequency dependent fading that the multipath emulator is designed to emulate, and that's shown here for the 5 gigahertz band, also the 6 gigahertz band in this particular case. A part of the 5, also the 2.4 gigahertz band. So we have all these measurements, again, also all available on our website. If you want to just look at this another way, if you have a system where you have a transmitter and receiver, and the receiver is seeing a signal at a certain level, you can see it up here at the top with no multipath emulator in the link, and then you just insert one in the link, but leave it in line of sight mode, so it's just in the link. You can see that we get about 15 dB just of loss, just because we put it in there. And then if we turn it on in non-line of sight mode, we get another 12 or so dB of loss. So this is the effect of the multipath emulator in a link budget. And then we have the same kind of data for everything, right? We have attenuators. So just again, even if we don't put the attenuator, even if we don't tune the attenuator to a certain attenuation, we just put it in and leave it at 0, we get loss. That's the insertion loss. And here's the measurement of that insertion loss for attenuators. Here is the measurement of that insertion loss for some of our splitters, 1 to 2 splitters, 1 to 4 splitters. Again, we have a lot of different of things, but all of those fall under that big bucket of stuff between the transmitter and the receiver, and you simply add up all of them in order to create your link budget. So you'll understand the full path loss by including all of those losses, and then you can create an end-to-end link budget. So the way we do that in our test beds is because we have a lot of familiarity with this. We have we have some kind of rule of thumb, simple ways of working through what that link budget should be. So, for example, typically in our chambers, when we're talking about the over-the-air part, again, I explained before how close that is to a free space model. Typically that adds something like 25 dB to the link budget. The multipath emulator I just showed you before, 15 dB or so of insertion loss in bypass mode. An attenuator here, 10 dB. A 1 to 2 splitter, 5 dB. A 1 to 4 splitter, 10 dB. et cetera, et cetera. There are all kinds of things dependent on how the system is configured, what you need to include, what you don't need to include. But once you understand the concept, it's fairly straightforward to do. So now hopefully we're getting to Naveen's question, right? So what we wanted to do was model a mesh. And I showed you before the mesh in the real world. We converted that using link budgets into path loss. And now we can understand how we can set up. So for example, here's our 3-node mesh, our red, our green, our blue. And we know that our red to green link was 79 dB. So if we just use the information that I've just been discussing, we know we've got 25 dB of over-the-air path loss on each side in each of these boxes. We've got an attenuator that just has 10 dB of insertion loss just all by itself. We've got a 5 dB because there's a 1 to 2 splitter in this part of the link in this PAL6. So we add all that up. That's 50, 60, 65 dB. We know we want 79. So to get to 79, we just turn our attenuator from 0 to 14. And then boom, we've got 79 dB of total loss between those two. So now we've got in our test bed a reasonably good model of what that mesh system link would look like in the environment in which it would be placed. So I'm going to stop here, and we're going to do a demo of this so you can actually see how this works in real life. So we're going to show you how the path losses work in our Stack Max mesh test bed. So first of all, this is the test bed shown here on the right. Those 3 chambers that I just showed you with the red, the green, and the blue, that's essentially the top one here. And then the 2 on the left with the doors open. These are the mesh, the mesh chambers. They're all connected together using these links that are shown here on the left of this diagram. So if we, the demo we're gonna do works a little bit like this. In this top chamber, we have a sniffer. And Anna, who's gonna talk about this, will describe this a little bit better, but we do have a sniffer. That sniffer is able to sniff anything that it can hear over the air. So it can sniff beacons from this red AP. And when it does that, it will receive them at some level. It can also sniff the beacons from the green AP. And when it sniffs those, it will hear them at a lower level. Why? Because it has to hear them as they pass through this attenuator, this splitter here, this 1 to 2 splitter, and another over-the-air link. And also the over-the-air link in this top box is actually a little bit longer. So when we add all that up, we have 25, 10, and then 5 and 5. So that's 45 dB of total difference. So what we would expect to see from this sniffer is that when this sniffer looks at the red AP, it's going to see something. When it looks at the green AP, it's going to see probably 45 dB less signal than that. So let's hand this over to Anna and see what that looks like in real life.
Okay, thank you, Lee. I will now share my screen. And here we are. This is what our test bed looks like in that full 3-node mesh configuration. As Lee described, our local access point 1 in chamber 1 connected via red highlighted paths with the access point 2 and 3 in the adjacent chambers. This time we have configured our PAL6 device as a sniffer. So it will be able to sniff the beacon frames from each of the access points here and also see and measure the received signal levels. Then we will capture those and compare and calculate the delta along each of the paths highlighted in red. We can also configure or control this path loss by, as Lee mentioned, our programmable attenuators. And in this demo, we will also demonstrate that. We have introduced the access point 4 and the path through the Quad 10E to our local chamber, and we will adjust the attenuation and this quadrigen to demonstrate how it works. This is all helping in emulating that real-life scenario with different path loss in different condition and with the distance between the axis point changing. So let's now go to our UI, that's 21st century software capability. And you can see we have our sniffer probe, pulse 6, and the Wireshark. So let's start the capture. Right here now we can see the captures coming through and populating. And you can see the beacon frames from each of the access points. These are the MAC addresses and then respective RSSI levels from each access point. You can see our pulse 6 as a probe ID. And I will go back to our UI and stop the capture. And then let's look at the results. As you can see, MAC address ending in 7124, which is my first access point 1 in the local chamber, had a neg 20 dBm RSSI. Let's go back here and capture. And from the previous measure, it was equivalent. So let's go check the second access point. So the EF04, this is access point 4, was at neg 63 dBm. So I'll go back. It's also consistent with the previous measure we captured. And 3084, this is my access point 2, had neg 63 dBm. So here we have a 1 dB change, and let's capture the last one. So 2F54 in chamber 3 had neg 63. And that's consistent. So now that we have recorded the measurements from this instance, let's check the RSSI level delta along this path from AP1 and AP3. So neg 20 dBm minus neg 63 dBm, that's 43 dBs. Then along this path, a neg 20 dBm minus neg 63 dBm, and AP2, it's 43 dBs. And along this path, neg 20 dBm minus neg 63 dBm at AP4, it's 43 dB. So as you can see, we're receiving consistent results in this type of configuration, and we are very close within 2 dBs from our estimated 45 dB that we like to always be the worst case scenario and conservative. So now let's apply the attenuation to quadrigen E and see how that changes our results. I'll go back to the UI, find my quadrigen here in the settings. I can, in example, add 10 dB attenuation. You can see, or you can move this lever. So let's capture. Going back to Wireshark. The sniffer probes are coming back up from the beacon frames, and you can already see there is neg 73 dBm along that path at the access point 4, but I will go and stop the capture so we can check the results. So here we are. There is no change for the other access points. Next 63 dBm for the access point 3, neg 20 for access point 1, and here for EF04, which is our access point 4, you can see neg 73 dBm. If we go back, that's exactly 10 dB delta that we have introduced. So this is how we manage and test and calculate the path loss and delta between the RSSI levels to emulate a real-life scenario. Please let me know if there are any questions.
Yeah, by the way, folks, we do take questions live. We do these seminars 3 times a day to reach all the time zones. That's because we like to interact with our audience. So feel free either to raise your hand or type your question into chat or into Q&A. And if you need help with Zoom, if you're new to Zoom, let us know and we'll help you do that.
Okay. So yeah, I'm hoping, Naveen, that got close to the answering the question you had. Oh, you raised your hand.
Naveen has a hand.
Excellent.
Okay.
All right, go ahead.
I am allowing you to talk. You'll have to unmute yourself.
Thanks, Lee. So it's giving the answer. So my another question is, so when we do all this configuration, which we are calculating by adding, so these all things we are doing manually inside a setup?
Well, I guess it depends on what you mean by manually. I mean, in order to model a specific or even a generic physical environment, yeah, you would have to kind of do the initial setup. But then other things, of course, can be done more automatically. Maybe this next demo will get at that as well. So, for example, Anna just showed how she could use the slider bar and change the attenuation. But of course, it's not necessary to actually do things via the UI and the slider bar. You can have the system do those things automatically. So maybe this next part will answer that part of your question. Let's see.
Okay. So another thing is, who define this link budget? So customer ask for different link budgets?
Oh, yeah. I mean, it could well be that, right? It could be that that a customer is saying, well, let's see, we have a 3-node mesh product. It's designed to cover a home of a certain size. So maybe they'll say like, well, then let's see what's kind of the maximum extent of of a home in the region that we're interested in. Maybe a U.S. home or a home in Japan would be very different, and the expectations would be somewhat different. But they would want to know that if a customer placed the devices at kind of for some reasonable sized home in that area, they place the devices this far away from each other, how it would perform. And so yes, I think usually it would be it might be an operator who is expecting to deploy this, or it could be an equipment vendor who has created a product that is expected to be able to support a certain kind of deployment model.
Great.
Again,
thanks.
Yeah,
Thanks,
again,
Lee.
okay, sure. Again, we don't expect people, I mean, usually, people aren't saying like, I'm going to model Naveen's house and I'm going to model Lee's house, right? People don't do that. They want to model a generic home, but they do want to understand that the product, is applicable for, a typical kind of scenario in whatever use case they're looking at. So, and then as far as, doing things by hand, let's talk now about, what you can do with this. So we just showed how you can set up a mesh. Anna just showed how you can have a mesh. You can change the distance between the devices to kind of cover any sort of mesh deployment you want to. But when you're actually testing a mesh, what you're really interested in is what a device will look like. What a device will see as it moves throughout this mesh. So in the real world, it would look something like this.
Excuse me, Lee, there's a
yeah.
question for Shweta.
Oh, okay.
And it says from AP1 to AP4, estimated path loss is 25 OTA plus 10 quarter 10 equals 35. How is it 45? Okay, so we have basically in this example computed the delta. Okay, so because we have one sniffer and the sniffer sniffs all the APs from its own perspective here. Now, we computed the delta that we expect the sniffer to see. Okay, so in the local chamber where the sniffer is sitting, it hears AP1 at something like minus 21, 22 dBm, very strong. But it also hears this high gain antenna that is in red there, right? A slightly lower signal because those two are across the chamber on different walls. So we gave it a delta of 5 dB. That's a local delta for the sniffer, okay? The rest of the numbers, like Lee explained, we have estimates which are conservative. We rounded them up to the nearest 5 dB just to make math in the head pretty easy. So that it's always a little higher than actual, and that way you'll be safe with your budget. It's a budget, right? It's not exact. So you've got 10 dB of attenuation plus 5 dB through PAL 6 plus 25 dB, right? That's 40 dB plus we gave it 5 dB delta over the air in the local chamber on top. And that's our estimate here. And so you can very quickly through any path in the chamber add 5, 10, 15, whatever, 25 in your head when you're just looking at a path. And that's what we use internally. That's what we settled on. And it's an estimate and it makes things easy. If you folks have specific questions, you'd like some help, if you're just starting out with the Octobox, send us a message and we'll step you through it.
Okay, and so to finish this up, right, then the question is, so how does this mesh perform? So device will move around, and it will be much more active. When we set up these links that we just talked about, they're sort of static because the mesh devices typically are not moving. But a user device, a station device, will move through the mesh, and at some point will be closer to one of the APs, then it'll move away, and then it'll be closer to another AP, and it'll move away and get closer to another AP. And we can do the same exact thing that we just described, except in a more dynamic fashion by changing multiple attenuators simultaneously, and essentially creating motion automatically without actually moving anything. And we can even include multipath in the link, for example, between a station and a device by including the multipath emulator instead of an attenuator. Again, as discussed in one of our previous demos. So for example, in this stack, we can use our stay pals, for example, as devices to roam through our mesh. Now, again, we've already set up our mesh as we just described using these attenuators. We can now use these attenuators simultaneously to essentially move the PAL across the mesh and then see how the device performs in the presence of the mesh. We can do it either with PALs like that, or we can do it using real devices. And again, same basic idea of multiple attenuators that let us simultaneously change the attenuation between the station device and the mesh nodes. So we're going to show you that as well. We've done this before in our seminars, but today we want to do it really to emphasize how we can modify the link budget to emulate roaming. So I'm going to hand this over to Radha to do that.
Thank you, Lee. So for this test, I'm going to show you guys how a roaming scenario works along with our synchro sniffer. So I'm running everything via automation here. So we have 2 access points set up here, one on 5 gigahertz, one on 2.4. And like Lee mentioned, we have our stay pads, the client device that's going to roam from 5 gigahertz to 2.4. We're roaming between 2 different bands, and we're using our attenuators to ramp and create a roaming scenario here. So this is how our UI looks like. So I'm gonna wait for the test to start, and then once the test starts, I'm gonna show you guys how the roaming scenario looks like with throughput and all the other statistics that we have. So I see the test is running. So the test is running, and the first thing, the client is connected to the 5 gigahertz access point here, and I'm using our software and automation to ramp the attenuator and increase the attenuation, so I can see that the device is moving further away from the 5 gigahertz access point. And as the device is moving away, I see RSSI is dropping, and I see the throughput is dropping. And along with that, we see all the statistics like data rate, MCS, the number of streams, and the bandwidth. Everything is dropping consistently. And once it's there, so now the device, the client is able to see 2.4 and 5 gigahertz access point, and then it's going to associate to the 2.4. It's going to roam from 5 to 2.4. So I see from the sniffer that I see all 2.4 packets on a sniffer. And here our RSSI is increasing because now the device is moving closer to the 2.4 access point. And again, while it's moving closer, I see RSSI, the signal strength is getting better, the throughput is getting better, all our other statistics like data rate, MCS, it's getting better and better. And once it's closest to the 2.4 access point, the script is again going to ramp the attenuators and emulate the client to roam back to the 5 gigahertz access point. So we can look at all of that over the software. So I see it's a peak point, and now I see RSSI is dropping, so I know the attenuators is ramping back. So we're increasing attenuation, and we're moving the client further away from 2.4 and closer to the 5 gigahertz access point. So let's wait while it's ramping the attenuators. It's going down slowly, and it's going to go up to like negative 90 dB for disassociation, and then scan for the 5 gigahertz access point and associate back to it. And while all this is happening, we can look at the sniffer captures here. We see all 2.4 gigahertz packets, and now we know it's going to disassociate in like just a few seconds here. And I see the throughput is 0, so it's disassociated, and there's no RSSI, so I know the client definitely disassociated. And few seconds for it to scan and associate back to the 5 gigahertz access point, and then we would see the throughput back up. So throughput is up. Now the device is moving closer, so we would see an increase in throughput and an increase in RSSI. This basically shows us how we can use our attenuators and ramp them for the client to roam between 2 different access points and use that attenuation and look at everything on the plot and with all the statistics here.
Thanks, Radha. I'm just going to grab this screen quickly because I know that we're just a little bit long, and I want to just wrap it up. But if people have questions, we always stick around. So that is actually the end. You know, again, what we tried to show today was, you know, explain the concept of a link budget in the concept of our test bed, how we can create complicated topologies like meshes and roam devices through them simply by manipulating the path loss between the devices. So that's it for the day. We're planning to talk in our next seminar about testing using the broadband forum TR398 test plan. If you've got other things you wanted to have us address, do email us and let us know. And as I said, we will stick around. We appreciate you all sticking around, but we will stay around for questions if there are any more. Oh, and in case there are not, just by the way, all of our seminars have been, hi Naveen, hold on. Our seminars are all being archived, and we have this list here of where they are. I think this is also on our website. So feel free, if you didn't see any of the previous ones, to go back and watch those. And Naveen, yes, what's up?
So it's a great presentation. So one more question I had. So you told about regulatory having different power levels as per the different countries, regions, right? So
Yeah.
in that case, so this path laws will be varying as per the different the configuration of the regulatory, right? So how we can control, how we can control all, how we can
Sorry.
control all this through our setup?
Okay, so just to be really clear, path loss doesn't change based on regulatory stuff. The only thing that the link budget does, I think that's maybe the point you're making. The link budget changes because the transmit power changes, right? So path loss is a component of the link budget. That's based on physics. The transmit power is based on regulation. So how can you control that? Well, again, the testbed itself doesn't particularly care. I think maybe if I'm interpreting your question right, it's like, how do I tell the device to operate in a specific region, right? Maybe is that your question? That again isn't something that we control, right? You typically it would be something like the device would be set for the European Union, or set for Israel, or whatever it would be, and then when the device is told that that's the region it's operating in, it would modify its maximum transmit power to conform to the local regulation. So the device has to know essentially where it is in order for it to behave correctly. The testbed itself doesn't do that.
Understood. So it's like we need to configure the AP itself, and then automatically testbed will take care of it.
Automatically the device should take care of it. I mean, if it doesn't, that's something that you can check. If it doesn't, that would be a mistake on the device's part. But the devices should always conform to local regulation. And I see a bunch of hands raised, so let's talk.
I'm Tiago. You can.
Yes, Tiago. Yeah, Tiago from Zebra Technologies, Bangalore team. So I have one question. I have two questions here. So one is so in the roaming scenario, what you guys shown, it was really good, and we really focus on client side. I mean, real client testing. We are involved into the real client testing. So we test with a different type of infrastructure. Basically, the AP vendors will be different. Okay, the question here is, okay, so you guys are using this antennas, right? Basically, the real client, you're keeping it in the box, and there are antennas. Antennas takes the signal out from the device and then get connected to this access point. So will this impact throughput tests? Basically, will this impact any of the MIMO capabilities?
No. So the test beds themselves are built to support MIMO capabilities. So maybe if this is the first time you've seen one of our presentations, we didn't do the detail here, but for example, this thing that I'm circling right now actually represents 4 antennas.
Okay.
This thing that I just circled here, that represents 2 antennas. So, and the reason it's 2 is because most station devices are 2x2. So we can support the maximum number of spatial streams in any link in these test beds. So if you're looking to make sure that you can do a 2x2 link, for example, between here and here, the answer to that is definitely yes.
Right. Okay. Got it.
So we have another question from JD. JD, you can go now.
Hi, can you hear me?
Yes.
Okay. I got a question to the physical part of the presentation. You did some measurement to compare the theory of the free space model to the actual values you can measure inside the chamber. And yes, exactly this one. And you did it with one antenna on the one side, where you altered the distance to, you said, two dipole antennas. Nowadays, a lot of the devices, especially mesh systems, go up to like 4x4 links. And this comparison between theory and real measurements, does it also held true for more spatial streams?
I mean, I believe it does. The environment, what we're showing here is that the environment in the box is basically free space. We have, you know, we've damped down reflections, so we're not getting, you know, we're not getting the effect of multipath from the box itself, and we don't have reflections from other elements in here, and of course the environment itself is not cluttered, so we don't have clutter. So essentially what we're saying is between any, you know, antenna, we're getting any set of antennas, we're getting a free space model. In order to support MIMO, we would have, let's say, 4 antennas here, 4 antennas here, and you know, I think what we're saying is that between any pair of antennas, we're seeing free space propagation. Okay. Which is true. That is in fact the case. It doesn't mean that we don't support MIMO. We do. That's actually the question just before as well. We always support, you know, the maximum number of spatial streams.
Yeah, sure.
That are available. But it's just that the link between any 2 sets of antennas is free space in the box.
Okay.
I have another question from Tiago again. Tiago, you can go.
Yes, Lai. Just a curious note, right? See, we talked enough about this path loss and path loss scenarios. Are we going to consider some of the Wi-Fi loss, like multipath or the MIMO loss due to the environment? Are we going to consider, or are we going to have those scenarios as well simulated here?
Yeah, I guess what I would say is if you didn't manage to see it, you might want to take a look at our first seminar, which actually talks about that sort of line of sight, non-line of sight conditions, which I think is what you're asking about, sort of multipath. So we do have an emulator. That's what this slide is talking about. We actually can emulate multipath in the chamber itself. We have this device that can go between a line of sight mode, which is shown in this upper part of this path, and then a non-line of sight mode, which actually generates multipath. So this is the frequency dependent fading. So
sorry, I will go through the presentation. Thanks.
Yeah. So
actually,
if you take a look at
and you asked about outdoor environment, so essentially you have customers using the Octobox for CBRS and LTE. So those are outdoor networks. So it all comes down to, like Lee was showing, modeling the path losses. Whatever you have outdoors, you have fewer walls, you would have different multipath, but you have in the urban environments, for example, you could have buildings and different multipath models. It translates into path loss. So when you're doing, for example, the full range of your link, right? The important thing is that you can get, like Lee was showing, the link budget from saturation to disconnection to below your sensitivity. If you have that full range in the test bed, you can effectively test indoor and outdoor links, if you think about it. And that's true in the Octobox. Our attenuators are 90 dB of range, and they will disconnect even for GLT, which is the most challenging, let's say, to disconnect at lower frequencies. So yes, it's usable for our indoor-outdoor links.
Okay, thanks.
Sure. Any more questions, folks? We are already 15 minutes over time. We definitely are happy you joined us. We will be repeating this session 2 more times. And if you have further questions or suggestions for topics, please email us. And we'll see you in a few hours.